Hello, hello, hello. Yeah, okay. Welcome, everyone. Welcome back to Brown for those who left for the summer. I'm Professor Kühne. I was the chair of the colloquium committee. So first of all, I wanted to thank the committee, Jennifer, Lucas, Stefan, Mike Koselitz, and Leo Lee. For the hard work, we have a full schedule, I think minus 1 or 2 slots for now for the whole academic year. So looking forward to seeing everyone attending all these events. Today is our first one. Jennie Traschen, I let Stefan Alexander introduce her. Welcome all.
Thank you. Thank you, Matthias, and the rest of the committee. I'm glad I'm not the chair this year. So anyway, on behalf of so our special guest here is co-hosted by Professor Lowe, sitting right here if you can't see him, and of course myself. And there's a good reason for that. And as I was thinking about what I'm going to say to introduce our speaker, very quickly, by the way, is the following scenario, which is, you know, oftentimes I sit on a rock and I look at the sky and wonder, what would success look like for me later on in, whatever, in my career? Well, don't ask that question, but it would probably look something like this, that I go away somewhere to give a talk, and there's a young graduate student there, and many years later, this graduate student becomes a professor, and in the interim, studies and base their work on that person's, I'm talking about this person's work, to the point where they and another colleague who is also influenced by their work invite them later on, 30 years down the line, to give a colloquium. Well, that person was, the grad student was me, and that professor is Professor Traschen, because I first met her 25 years ago when I was a graduate student, and I remember being very impressed with her because my PhD advisor told me that back in the days at Harvard, where she was a graduate student, and a person named Alan Guth was writing the seminal paper that sort of brought together ideas in particle physics and cosmology called cosmic inflation. There was a secret group of grad students that met behind the backs of professors at Harvard to study these papers. And so Jennie, Professor Traschen, was one of the pioneers of the field that I sit in, called particle cosmology. She's also a renowned relativist, and of course that's with Professor Lowe. So we came together and said, with the help of the committee, we got to get her here. And on that note, Professor Jennie Traschen.
So, thank you very much for that kind introduction. I was a little confused about where I was 30 years ago, where I am now. And I also want you to know that I spent a reasonable amount of time trying to get the colors lovely, as if I had gone to RISD down the road. But for some reason, they come out looking like this. So please do a translation in your mind. Pretend that this is, what is that? Feng shui or shui feng or something. Anyways, okay. Yeah, so I'm Jennie, and what I'd like to talk to you about is, I didn't sit down and do this work, well, actually a sequence of papers, because I was thinking, okay, I'm going to crack quantum gravity or contribute to that endeavor. I noticed some stuff about the thermodynamics for black holes in de Sitter, which is a positive cosmological constant, and over a couple of years' time, came to identify that thermodynamics with the thermodynamics of a spin system, very simple system, non-interacting spins in a background magnetic field. Each spin can be either up or down. So it was a very simple system. And I thought it was interesting. I hope you also will think it's interesting how much you can get out of the comparison. So that's the abstract, and the punchline's at the bottom, and we'll come back to the punchline when it comes up. To a large extent, this research has been done with a number of undergraduate students at UMass, some graduate students, and Patrick Draper was a professor at UMass. Now he's at Illinois, and David Castor is a professor at UMass. And I've just listed a few names. I'm not giving an exhaustive set of references. You could never read it. but a number of people who have worked in kind of adjacent areas. Okay, so I'm happy to give more detailed references for anyone who's interested after the talk. So this is kind of a longer introduction. It's going to introduction and outline in one. The introduction starts with a little story. A student, Jack Dinsmore, came to my office and showed me these plots for a black hole, non-rotating black hole, just a Schwarzschild black hole in de Sitter, which means a positive cosmological constant. The first plot is, the cursor does show up, okay. Is the area there refers to the total area of the sum of the black hole area plus cosmological. This is very fast, introduction, and then I'm going to go back through this stuff. Anyways, it looks like this. It interpolates between two plateaus, and if you take the derivative, there's a peak. So this was not something I was familiar with, and it's certainly not the way that thermodynamics looks for asymptotically flat black holes. So I asked around my condensed matter colleagues and said, well, does this look familiar? And finally I got an answer that yes, that looks like the entropy and the energy for a two-state system. So you have n particles, each one can be in two states, and the entropy has this kind of saturation property of interpolating between two constant values. And so the derivative has the accompanying property. So you can see, if you think about two states in a, what's that called? Canonical picture, it's simple to see, or straightforward to see why this would be the case. If you have a higher energy state and a lower energy state, those two states, if the temperature is very low, then all the particles are in their lowest energy state, and lowering the temperature even further doesn't change the distribution. On the other hand, once the temperature gets high enough, bigger than the gap between the energy of the two states, then there's an equilibrium between numbers of up and down, or they're transferring between the two states. And again, raising the temperature doesn't change the equilibrium. I hope that's not my phone. It's okay. I never learned how to turn mine off. Okay, so I did this work with on the Schwarzschild de Sitter SDS model, and it had some interesting successes in comparing the black hole curve, the area, versus the surface gravity, which is identified with the temperature, and the StatMech model. See, they look kind of the same shape. And that model had some successes, but there were certain things that just didn't match. And I felt that fundamentally, those things that didn't match, you would always kind of end up with this black hole instability. So for a Schwarzschild black hole, when the black hole gets very small, for a Schwarzschild de Sitter black hole, when the black hole gets very small, its temperature goes to infinity, and you have the same instability that you have in asymptotically flat space-time. The cosmological constant doesn't cure this mass going to zero problem. So I was a little bit embarrassed some years later to remember what I should have remembered sooner, that I also knew, so this was actually earlier work that I did with two undergraduates. Gautam Satish Traschen is now studying gravity, except at one of the institutes at that place, Princeton. And James McNerney has moved to soft condensed matter theory. And one of the things we did was to look at the cosmography, I called it, of rotating black holes with a positive cosmological constant. So you add rotation to the black holes and charge if you like. You can get the charge added for free. Now, I want to compare that to what a microcanonical description of the same spin system that we were talking about looks like. In the microcanonical description, the entropy as a function of energy first increases and then decreases. And I'll go through this in a little more detail. I do realize that for some people here, some of this is super basic, and then other parts of it will be super basic for other people. That's the breaks. The temperature being 1 over the temperature is the slope of this. You can see that the temperature on one side is positive and one side of the curve is negative, and because it's 1 over the temperature, it goes to infinity in between. So I was thinking about this and I'm like, oh, well, these two curves look kind of the same. All right, where are we? So one of the things that was added in this present work, which is coming in the talk, is that we introduced a very relevant surface gravity for the whole system, or a temperature for the whole system, which looks qualitatively like the temperature versus energy graph for the spin system. So this is kind of where I'm headed. I want to introduce these comparisons more slowly and tell you what you can learn from examining this. Okay, so I asked the basic question, does this similarity have physical meaning? And I claim that it does have physical meaning, and that's what I will talk about and hope to convince you of. All right, so there's an outline. Basically, we're going to start and talk about horizons, because all this area stuff is the area of horizons, so I would like people to know what the horizons are. And then introduce some properties of rotating black holes with cosmological constant, which was something I never thought I would get interested in. I mean, I haven't written down the metric. I won't write down the metric. There's just, why would you want to mess with that? And then switch gears and talk about the basics of the spin system and compare those. And then we'll find out that it would be possibly advantageous to move to constrained subsystems of spins so that we can make comparisons with the black hole and the cosmological sectors. And then we'll end up getting a relationship between the number of spins and the parameters of the rotating black hole spacetime, which is the mass, lambda, the angular momentum, and the charge. And then I'll conclude. And I'm happy to take questions more or less any time. So, black hole horizon. I have on these cartoons a kind of a way to think about what a black hole horizon. So there's a sequence of 3 spacetimes here. We start out with the sun on the top of the spacetime. The sun has some mild curvature, but basically spacetime is pretty flat. And I've indicated the important thing is these little arrows. So time is up, space is horizontal. If you're a relativist and then you try to teach mechanics, especially like intro mechanics, right, this is very hard to get your pictures going, right? All right, anyway, so light rays can go inward or outward. If that sun collapses with the same mass, collapses to a neutron star, so the mass of the sun is concentrated in something that's like the radius of 10 kilometers, then something interesting happens. The light cones tilt preferentially towards the star, towards the center of the star. So it's there's less angle for light to get out than to go into the star. And a black hole horizon is a limit in which the light cones tilt so much that on this picture, one ray, the outward ray, is propagating along this vertical line, which is the horizon, and the other ray of the light cone is going inwards. So these are kind of funny coordinates for looking at light propagation, but one thing you can read off of this picture, since I've put a light ray going along the horizon, is that the horizon is a null surface. Light rays can propagate on the horizon, but anything with rest mass can't stay on the horizon. And once you get inside this kind of shaded region, the light cones only point towards the interior. So once you go inside, light cannot escape, and nothing else does as well. Okay. So a black hole separates the inside from the outside. In order to define a black hole, you need a notion of what you mean by the outside. And Hawking first defined black holes for asymptotically flat spacetime, so you need a notion of an asymptotically flat region. And if you're changing your asymptotics, like adding a cosmological constant, then you have to, again, say what you mean. But for our purposes, it's this null surface. It separates the inside from the outside. Classically, things only go in. The geometry of these, the simplest black holes, and here I've drawn a picture of a static black hole. The geometry, so H is for the horizon, B is for black hole. The black hole is characterized by an area. So in this, it's an area of a two-sphere. And there's a local geometrical quantity, which I'll denote as kappa, following tradition, which is called the surface gravity. And that's something that you can compute on the horizon. As I said, it's a local geometrical property. All right, pause. You might ask, can the inverse happen? Can we have something where things only go out and not in? Well, yes, that's a cosmological horizon. Okay, so here's a kind of a similar cartoon picture, but now I'm showing the light cones tilting the other way so that you have this finite range of radius of spatial distance, and then the light cones all tilt preferentially towards the asymptotic regime. So this is a horizon that's going the other way. So if you take this cartoon and look at it as a constant time slice, and because of the static, every time looks the same as every other time. So here's the interior, and us, US is for us, not for US. Okay, but they get spelt the same way. I should have said, we are here, like one of those maps. Okay, you are here. Okay, so this is us. And if we're keeping ourselves in this region, you can only go out of the horizon, but someone that starts in the exterior of this ball can't come in and chat with us. Okay. Now, this is a horizon. It's also a null surface. So again, I've drawn a light ray propagating on the boundary. And it has the properties that it has also an area, so A sub C for cosmological. And again, you can compute this property, which I haven't defined for you, but you can compute it. The surface gravity. For de Sitter horizons, the surface gravity is negative. It comes out to be negative. Okay, I've added a few comments about formation of a cosmological horizon. We understand that black holes form from gravitational collapse, and that's something that we might have some feeling for. Cosmological horizons of the sort I'm going to talk about can form, for example, or apply to a universe with a positive cosmological constant. So if you have the right combination, right relationship between the energy density and the pressure, you form this kind of cosmological horizon. And of course, positive lambda, although it's harder for quantizing gravity, here does come into cosmological scenarios, two very different energy scales, so people contemplate the existence of a cosmological horizon. All right. Then, of course, the last step is to combine the two horizons. Yeah, you have two interesting things. What could be better than null surfaces? So now we want to combine them. So in this picture, the kind of shaded region is the interior of the black hole. And then you have the us, this is where we are. And then you have another null boundary, null light boundary, so that on the spatial slice over here, if we draw a spatial slice across the diagram, the black hole is in the interior, and I've put some little arrows there showing things only go from the us region, things go into the black hole. And from the us region, things can go out into the cosmological. Otherwise, observers who stay in the region us are isolated from the rest of the universe, since they don't get any information from inside the black hole, and they don't get any information from outside the cosmological horizon. Okay. Of course, if you decide not to stay in this in-between region, you can go into the black hole or go into the cosmos. All right. Now, when you do this, when you have a black hole with positive cosmological constant, some of the properties are quite different. And it's because of these two horizons. So first of all, there's a maximum mass, and I've given its value in terms of lambda, as opposed to asymptotically flat or asymptotically AdS, negative cosmological constant. Mass is not bounded. The total area I will talk about as the sum of the areas of these two horizons. So in this spatial slice, that means the area of this smaller sphere and plus the area of that larger sphere. So you add them up, and that's the total areas in horizons. I've also put on this slide some of the connections with black hole thermodynamics. So the total area is proportional to the entropy in the interpretation of gravitational thermodynamics. And in units where G and H bar equal to 1, then the total area is 4 times the gravitational entropy. The surface gravity, which is why I mentioned it, is identified with the temperature. And it was Hawking's calculation of black hole radiation. You have a quantum field that radiates with the appropriate kappa as the temperature that really made this analogy a physics analogy. And just a reminder for the black hole that its surface gravity is positive, and for the cosmological horizon, its surface gravity is negative. So people react different ways when they see negative temperature, but as suggested in the title, did anybody notice that in the title? As suggested in the title, I think this is actually a place where all of a sudden I realized, okay, this is the negative temperature. The negative sign is actually tells us something. Okay. Now, part of the analogy, what made the analogy between black hole mechanics and black hole thermodynamics, is the first law. I've written the first law here in truncated form, meaning at fixed. Well, it's not that truncated because this is short. So at fixed lambda. So we're used to thinking of the cosmological constant as a constant. So at fixed constant, fixed lambda, you can prove a first law for each horizon. Okay. So the first law has the form, and I said down here in this kind of, it looks really, everything is kind of purplish on this big screen, which is a little sickly, but it breaks. That the change, you just read these as a change in the mass is the temperature times the change in the entropy. So there's two such laws. One so H refers to horizon. For B and C, black hole and cosmological, that they have exactly the same form, that the change in the mass is kappa times the change in the area, either black hole or cosmological, with an 8 pi in the right place. So you have two such first laws. But the delta M is the same delta M. The mass is defined far away from the black hole at infinity. All right. Now, I've drawn for you a picture of how the temperatures or the surface gravities behave. So I've labeled that temperature. I probably should have labeled it kappa. So there's two curves on this plot. One is the red one for the black hole temperature, and it's red because it's hot. So as you go to smaller and smaller mass, the surface gravity of the black hole goes to infinity. For small mass black holes, on the other hand, we go to this blue curve, which is cooler, the cosmological temperature, and that's some constant determined by the cosmological constant. And then those two temperatures, those two surface gravities both go to 0 at the maximum mass. Okay. So I've written that over here, that we have these two surface gravities, and that both of these surface gravities go to 0 when the two horizons merge at the maximum mass. I'll come back to this merging in a minute. That merging of horizons is called the extremal limit. Okay. So on the other hand, at the other end, at the small black hole end, the black hole temperature goes to infinity, and we have this black hole instability. So this is the black hole instability that I referred to briefly when I said that not everything in the Schwarzschild-de Sitter, matching that space-time, the thermodynamics, to the spin system. If you fix things so that you got one thing to match, then something else wouldn't. And then if you fix that, then the other thing wouldn't match. And I felt that that was fundamentally due to the black hole instability. You just weren't going to get that in the spin system. Okay, so that brings us back to the introduction. So the temperature behaviors fundamentally disagree between the black hole and the spins. But then something else that I knew is that rotating charged black holes actually have well-behaved temperature. Okay. So now, to Schwarzschild-de Sitter, we want to add rotation, angular momentum, and charge. You don't actually need both rotation and charge. And I preferred to think about just the rotation because then it's just a geometrical problem. But you can carry along the charge at little cost for these set of comments. Is that a fire alarm? It sounds. It should be for like your pizza is ready or something. Okay. All right. So the thing that's nice about having rotation and positive lambda is that you're going to get a nice bounded problem. Okay, so there's two horizons. Well, there's actually three horizons. Kind of snuck that one in. There's an inner horizon, which is not drawn on this picture. Right. So there's actually three horizons. We talked about the black hole and the cosmological. And there's an inner horizon that's due either to the angular momentum or to the charge or some combination of them. If you look at the limit in the black hole parameter space when the inner horizon approaches the black hole horizon, then you find that the black hole surface gravity, instead of going to infinity, goes to zero. So that's nice. I mean, that's also true without any cosmological constant. If you just look at a charged and rotating black hole in asymptotically flat space-time, when the inner horizon and the black hole horizon approach each other, then the temperature of the black hole, instead of going to infinity, goes to zero. There's a minimum mass at this point, at the point in parameter space, okay, and that's non-zero, and a minimum area of the black hole that's non-zero. There's another extremal limit or coinciding of horizons that we can consider, and that's when the black hole horizon coincides with the cosmological horizon. So I've written that here. When the black hole horizon coincides with the cosmological horizon, then both of the surface gravities go to zero. They're coming from other directions because one's negative, one's positive. And that point in parameter space defines the maximum mass of the black hole. The black hole horizon is going out. It's pulling the cosmological horizon in. That's as big as the black hole can get. That's its maximum mass. Okay. So the upshot of having these three horizons is that the mass and the total area, where by total area I mean the sum of the black hole and cosmological, both of those quantities are bounded above zero. So the minimum mass is greater than zero, and the minimum total area is greater than zero, and they're also less than some positive maximum. So here I've drawn a cartoon of how the temperatures grow. The black hole temperature now is very nice. It goes from zero to some maximum and then back to zero again. And the cosmological temperature at small masses starts at something that's fixed by the cosmological constant and then goes to zero. So this is a much nicer system to be dealing with. Now, if you've had the joy of working with rotating black holes or rotating black holes with cosmological constant, there's more things that you want to know than there are parameters of the metric. The metric is 4-parameter system, but you might like to know a lot of things, like the 2 surface gravities, the rotation I haven't written down here. There's more things that you'd like to know, formulas for, than there are parameters in the metric. So what you have is this very convoluted algebraic system. I mean, you have all the formulas, but it can be quite difficult to say, well, as I vary this and keeping these fixed, how things go. So working with James and Gautam, what we did was to reparameterize the system with this kind of interesting variable, or it's a parameter. I don't know, X probably in retrospect isn't the best name because it's not a variable, it's a parameter. But I guess I was short of names. So there was this product of the 2 radii. RB and RC are the radii for the horizons, and the areas just go like those quantities squared. That this quantity X is the product of these 2 radii. And we have 4 parameters in our metric. We're going to still use charge. A is how the metric is written, angular momentum per unit mass, lambda, and X instead of M. So M gets chucked, and we use capital X. And then the nice thing is that all the geometrical or thermodynamic quantities of interest can be written as functions of these 4 parameters. Okay, well, that was, okay. The formula for the total area then is very simple in terms of capital X. And not only is it simple, it has a symmetry. I wouldn't even say any symmetry that you find for this is by definition interesting. So it has this symmetry, and you can see that it's basically X goes to 1 over X, all right, or more precisely, X goes to A squared L squared over X. So again, A is the rotation parameter. So that means that there are 2 distinct spacetimes. They have different values of X. They have the same total area. And here's a picture of 2 such spacetimes. So one of the spacetimes are the red graphs, and then the other spacetime that has the same total area is the blue dotted graph, or whatever color it comes out there. Okay, so that's an example of 2 spacetimes, same total area, think entropy, but they're different spacetimes, different masses, different X. Oh, I should have said that even though we've exchanged M, the mass, for X, M is monotonic increasing in X. So increasing X, you can think increasing mass. Okay, nice. All right, so again, here's the picture, the symmetry of A, and that corresponds to this plot of the total area versus X or M. And again, the way to read this is like, pick your favorite area that's less than the maximum. So that's my favorite area, whatever that is, and draw a horizontal line, and there's 2 intersections, 2 different masses, so those are 2 different spacetimes that have the same area. All right. I'm also commenting, because we'll need this later, is that the symmetric, what we call the totally dual, meaning a spacetime and its dual, the symmetric plot only applies to one curve in the black hole parameter space. So the black hole parameter space, you get charge, angular momentum, X, cosmological constant. In other portions of the parameter space, that you get different plots of what the total area looks like as a function of X. So not all places does every spacetime have a dual. So for example, if you look at this middle plot, if you can, if I pick a low value of the total area, then there's a unique spacetime with that. Whereas if I go to a higher value of the total area, there's 2 spacetimes. All right, so the parameter space is fairly rich, which I'm not going to explore all of it. I'm sure you'll be pleased to relieve. On the other hand, you might recall that this plot of area versus x or m looks qualitatively similar to the plot of spins versus energy. Speaking of spins, would somebody please speak of spins so that I can speak of spins?
You mentioned spins.
One of my favorite words. Okay, so very basic spin system. We have n spins, n is fixed, in a magnetic field. Spins can have two states, spin up or spin down. The higher energy is spin down, and that's denoted by a minus sign. Okay. So the total n can be divided into the number down plus the number up, and you can write the energy as a function of the fraction of spins down. For people who are used to working with this model, I think that I've used the opposite notation than is perhaps common in the stat mech literature. I think the parameter x, which is the number up over the total, is more common. But the nice thing about this parameter, anyways, when you see lambda, the energy increases with increasing lambda. So we're going to want to compare things where the energy is increasing to the right of our plot with the mass increasing. All right. So then it becomes, this is working in the microcanonical ensemble, which I like for gravity. Because there's no, in the canonical ensemble, you're always thinking about like just some heat bath that's there, like influencing my system. But if you're talking about a space-time, there's no outside. So conceptually, it seems, I always have problems with the outside. It seems microcanonical is interesting to think about. Anyways, this is in the microcanonical ensemble. What you parameterize the states by, say, the number down, and you count the number down, and then in a large n, everything, all numbers large limit, the entropy, which is the log of s, has this form. Okay. So you can see from this formula that if you interchange lambda, the down fraction, with 1 minus lambda, then the formula for the entropy is unchanged. And that's drawn in this graph, that the entropy as a function of lambda has a symmetry, the interchanging lambda and 1 minus lambda. And that's because in terms of counting the number of combinations, the number of states, so to get this omega of n minus, and really for counting the number of configurations, we could just as well call that n plus. So the counting doesn't care if you're calling up, down, or down, up. But we start out with a difference in terms of the energy, that parallel or anti-parallel to the magnetic field makes a difference in the energy. Okay, so that's why we have the symmetry here. You know, which is interesting to remark on if we want to see if we can use that, the obvious insight or fairly clear understanding in the simple stat mech system, if we can use that to try to understand what's going on in the black hole system, right? Okay, so, and then, as I said at the beginning, that the slope of this, the entropy as a function of energy changes from positive for lambda less than a half to negative for lambda minus a half, which means the temperature changes sign. Okay, so that's what I've said here, that the temperature, and here's the formula for the temperature, that's going to change sign and go to infinity at the top of the curve because it's 1 over the temperature. The slope of the curve is going to 0. So that's where this picture for the temperature of the spin model comes from. Okay, so you have a positive branch, a negative branch, and going to infinity in between. Positive, negative. Okay. So we observe that the area versus the mass curve looks a lot like the entropy versus energy curve. Kind of go up and down. But the temperatures aren't matching. Here's the temperature for the spins, and here are the black hole and cosmological temperatures for the black hole system. So I made this big song and dance about how the black holes are so much nicer because with the rotation, cosmic constant, it goes from zero to zero, and nothing's blowing up. But these two pictures don't look at all the same. Okay. All right. So I very slyly, I hope you appreciate how sly this is, the temperatures don't match yet. Okay. And the hint is that this is the kind of classic apples and oranges things, or peaches and pears, that this is the temperature for the whole spin system, whereas what I'm plotting here is the temperature of some subsystem, two subsystems of the space-time, the black hole and the cosmological. So what we're going to do is the black hole cosmological system kind of came to us with two easily identifiable parts. We have the cosmological horizon, we have the black hole horizon. They each have their area and their surface gravities. So let's look and see, well, what would play the role of a temperature of the whole system? Okay. Well, if it's the temperature of the whole system, it has to apply to if we're doing a first law, then we want the change in the mass to be proportional to the change in the total area, not just one area or the other. So the two first laws, I said each horizon gets its own first law, and you can rewrite them as the change in the mass is proportional to the change in the total areas. And you can, it's blah, blah, blah. It's simple, it's easier to write down than to say, apparently. The coefficient I've called kappa, the surface gravity for the whole system. And what comes out of the algebra is the sum of the surface gravities over the product. Oh my goodness. I think I have that upside down. Because, I mean, dimensionally it's wrong. Yes, I have this upside down. Okay, sorry about that. Right. Kappa has dimensions 1 over length, so it has dimensions. And it would keep the dimensions if this is flipped over. Okay. Sorry about that. I just noticed that now. Okay. So now what we want to do is to look at what this kappa system looks like, except look at it when it's written properly. Okay. And I've also changed my variable along the horizontal axis, independent variable, from x to y, where y is just a log of x. And then x has the symmetry, x goes to 1 over x. And so in y, with the logarithm, then the symmetry is y goes to minus y. And you can see why you like to try to do that makes it more like the symmetry in the spin case, which is just a shift. Lambda goes to 1 minus lambda. Okay. So when you do that, and you write down the correct expression, and you plot kappa system, then it does look the same as the temperature for the spin system, except it's shifted because my y parameter is shifted relative to lambda. Okay. Anybody, before I eke out a correspondence, are there any questions? Gosh, you people are quiet. Okay. So we can pause and say, well, what can we learn? Can we make any correspondence between the spin system and the black hole system? Right? What you would really like to know is, like, well, what do the n correspond to? What does spin up and spin down correspond to in the black hole spacetimes? So I'm asserting that there's this qualitative agreement between the total area and entropy and what I've called the system surface gravity and the temperature for the spin, between the spins, and that now I've written for the totally dual spacetimes. So totally dual spacetimes, here's a picture of the black hole parameter space. That's charge and rotation parameter. The picture's for fixed cosmological constant. So the totally dual black holes are just that dark curve. It does look like a darker curve in the parameter space. Okay. So for that portion of the parameter space, what we do is to equate the area with the entropy, the two systems, okay, with the right numbers of fours and h bars and g's. So now I've put in the h bar and the g. So on the spin side, the maximum entropy minus the minimum is n log 2, the minimum being 0. In the black hole side, the area never goes to 0. So what we've done is to take the difference between the maximum and minimum area and equate that. The minimum is very small compared to the maximum, so it turns out actually not to matter. And that gives this expression for n, that n goes like 1 over the square root of lambda, and then in the numerator, it's a squared plus q squared. Okay, where again, little a is the rotation parameter in the metric, and that's the angular, the ratio of the angular momentum and the mass. Now, that portion of parameter space is bounded away from a very small mass black hole. The very small mass black holes are down here, or very small charge angular momentum. So it would be nice to be able to make connection with something that's close to a very small black hole in de Sitter, right, which this is not yet connected to. So to extend the parameter space, what we did was to look at constrained states of spin systems. And in this, I'm going to go through this quite fast. We divide the spins into subsystems. We'll call some of them the B's and some of them the C's. So the total number is the sum of the B's and the C's. And the B's can have themselves be invited. The number down can be divided into the number of B's down plus the number of C's down, and likewise for the number of ups. And then you get two of these degree of upness or degree of downness parameters, that lambda is n minus over n, but each one gets a subscript, either B or C. So now we're going, for the spin system, we're going to get out two temperatures, one for the B's and one for the C's. And you divide the energies into the energy of the B's plus the energy of the C's, and then the temperature for each subsystem is defined in the usual ways. 1 over the temperature is a derivative of the entropy of that subsystem with respect to the energy of that subsystem. Okay, so the strategy here is to take for the B's, I called them B's. That must be because I want to identify them with the black hole. You take the lambda B for the B's to be less than 1/2, which is a positive temperature branch, and the lambdas for the C's to be the negative temperature branch. And that tells you something about what the fraction of upness or downness in the B's or the C's are. Okay. So one very interesting interesting difference, anyways, an important distinction between the spin system and the gravitational system is in the spin system, the energies add. You have the B's, you have the C's, and the total energy is EB plus EC, and nobody jumped up and down and objected to that. But in gravity, you can't do that, okay? That there's no way to localize the mass of the gravitational field, and the mass is defined at infinity, okay? And that's why in the first law, we have a first law for each B and for each C, AB and AC, but it's the same delta M. So this tells us of all possible subsystems of B's and C's of the spins, we already know to one condition, we're going to take lambdas for the B less than a half and lambdas for the C greater than a half. Another condition is that when we're going between different configurations, so microcanonical, but if we're changing the energy, that as we make that step, the change in the energy for each of those has to be the same. So with that, so here I've written it correctly, with that relation, the formula for the system temperature comes out the same as the system surface gravity, because you've put in the black hole physics here, that it's the same delta M, it's the same delta E. So here, got the formula the right way around. So given the time, I think that I'm not going to say more about the constrained substates. You can try to, the game is to try to match the spin behavior of the spin systems with the behavior of the black holes and see, like, how do these spin systems, the B's and C's, how do the subsystems, what properties do they have in terms of the parameters that you set up? What properties do they have that will give me back the way that the black holes act qualitatively? I mean, you don't want to you try to get too much matching, because this is a very simple spin model, right? So you don't want to try to squeeze more out of it than makes sense. So what I did was to match it. There's certain points in the geometry that stand out, in the phase space that stand out, that when the minimum mass, when the inner horizon and the black hole horizon get close to each other, the maximum mass when the black hole and cosmological horizons coincide. And the other interesting point is that top of that entropy curve, or the top of the area, the maximum entropy, maximum area. And there, the magnitude of the temperatures are the same. I mean, kappa C is negative, but its magnitude is the same as. So that's also an interesting point from the point of view of thermodynamic equilibrium, possibly interesting. So what we did was to look at those specific points and match the behavior of the spin system with the gravity system. And in particular, what we found is that you get a larger parameter space that you can compare the black holes to the spin systems. So that by doing this comparison of the entropy in one is the same as the entropy in the other, we're able to do that matching for black holes that have very small areas, so that you're getting close to de Sitter with a small black hole, to black holes where you have comparable sizes, parametrically comparable areas in the black hole and cosmological horizon. And what we found is that the number of degrees of freedom, which dimensionally, if you just have lambda, this is what you'd write down, 1 over lambda, with the right number of G's and H bars to make it dimensionless, is that you get an interpolation from this expression 1 over lambda to this other expression that I showed you before that goes like 1 over lambda to the 1/2 with a squared, or with a in the numerator, which makes the dimensions correct. Okay. Concluding remarks. So the takeaway is that there's qualitative similarities between the area as a function of mass, the system surface gravity as a function of mass, and the corresponding qualities of this simple spin, n spins, magnetic field, spin up, spin down. And that equating entropies gave us the expression for what n, the number of degrees of freedom, corresponds to. I think that one of the things that you gain by going to positive lambda is this, what you gain is having the mass bounded and the entropy bounded. And, if this analogy holds water, then the analogy with the number of degrees of freedom and a more microscopic version of gravity, then I'm not saying like that you need a cosmological constant, a positive cosmological to see that, but I feel like it's a little bit like considering a system in a box. That there's things about considering photons in a box that are simpler, and that's kind of what the Sitter, the positive cosmological constant, and the mass and the charge and angular momentum do with us. The way I view this is that it's suggestive. It provides evidence that there's an underlying finite substructure. So this work does not like try to say, I'm not taking a spin model and adding interactions and saying, well, let's see what really happens with black holes as endpoint of black hole evaporation. This is more like saying, well, wow, there is actually evidence in the classical gravitational behavior that suggests that there's this underlying finite structure. And then there's lots of things that you could keep on working on. So if anybody was paying attention at the beginning and reading the title, really this was carefully structured. Like, any of us that are old enough to have gone to the dentist and you had in the waiting room, you have those books and they were things that you had to find that were hidden pictures. Did anybody else? It was only me that did that? Okay. You had to find them. Well, as I should have said on the first slide, well, there's something hidden that's going to come up again, so you can find it. So that's there. All right. That's it.
All right. Thank you, Professor Traschen, for a very interesting colloquium. I imagine there are questions. Yes.
This better be a nice question.
It's a nice question. So if you fix lambda, is n independent of the mass?
Yes.
Okay.
So in the pictures that I drew, the mass was, all those graphs, all the plots, were pictures for fixed lambda, a, and q, and then sometimes we would go to a different a and q, and the mass would vary. So the way to think about that is that, so that the n only depends upon a, q, and lambda. Okay. And then you have to, the game is that you get different masses by something being different. But that's the same as in the magnetic field, right? You start with the n spins, and you get different energies by monkeying with some more of them are up or down.
Okay. Good.
So that what I would love to be able to say is what corresponds to spin up and spin down in the gravitational model. And I have different conjectures, but in a way there's too many twos in this problem. There's two horizons, and there's the fact that each horizon divides things into an inside or an outside. So as I went through the song and dance about horizons to try to put in your mind the idea that this is an exclusive choice, inside or outside. Now, you can go the other way, quantum mechanically, but there's a real distinction between being inside and outside. So there's those two pairs of twos. And I'd love to hear people's suggestions for what actually is the analog of a spin flip. The symmetry, I think I understand, the lambda going to 1 minus lambda in the spins and what happens in the gravity. But
Okay, other questions? Yes.
Thanks for the talk. I was just wondering, these calculations, how many dimensions are you in?
This was all for 4.
So do you think things will change if you're allowed to add more charges or angular momentum or something? Do you expect it to no longer be a two-state system?
Well, so that's a good question, and the honest answer is I don't know. I think that there'll always be something in the phase space that looks like this. So I didn't come back to talk about the Schottky anomaly in the rotating case, and that's because with the more dimensions in the parameter space, that you get different kinds of behavior. So I would imagine it's even more different. And the Schottky anomaly, again, is indicative of something with a fine n degrees of freedom and 2 options.
Okay, maybe a last question in the interest of time. Yes.
Really enjoyed the talk. Thank you. So, as far as I understand, you made an analogy between